Hi, Chem 151 students. Welcome back for the second lecture about transition metal compounds and transition metals. So we're going to start to talk about coordination compounds now. And these are very commonly made from transition metals when they're in aqueous solution. And they result in many interesting compounds. Most interestingly is they are colorful. As you guys know, very few compounds are colorful. And this is due to the fact that in order for a compound to be colorful, it has to absorb light within the visible spectrum, which is a very narrow part of the electromagnetic spectrum. So there's not a lot of compounds that do that. There are some organic dyes, and you'll learn more about why organic compounds can be colorful, probably in organic chemistry. But in general chemistry, we'll talk about why many compounds containing transition metals are colorful. But first, in this lecture, before we get to that, that's going to be the next lecture. In this lecture, we're going to describe how those compounds are formed, what atoms are in them, the way the atoms are bonded, and how they are named. And so that's going to be the focus of this lecture. Okay, so let's begin. We'll begin with some terminology here. First of all, a coordination compound. What is it? It's a compound in which you have a central metal ion, which is a transition metal, and it's attached by a group of surrounding molecules. And these are attached by what are known as coordinate covalent bonds. So we'll talk a little bit more about what is meant by a coordinate covalent bond, but those molecules which undergo a coordinate covalent bond with the central metal atom are referred to as ligands, or metal ion rather, sorry. And there is one atom on the molecule that is the ligand donor atom, and that is the atom that attaches directly to the metal. And based on the number of ligand donor atoms that surround a central metal ion, you'll have a coordination number. Now, most ligands have just one ligand donor atom, but some ligands have more than one. And so when more than one atom can attach, then you can have multiple attachments from the same molecule. And we'll talk about what that means there. But here's some examples of complexes with their coordination numbers. So this is a silver with two amine ligands here. And so it has coordination number 2 because each of these amine ligands attaches only in one place. And these are all going to be what are referred to as monodentate ligands. So they're ligands that only attach with one atom. We'll talk about polydentate ligands in a moment. But the coordination number is the number of atom attachments, basically. So here there's 3 iodides attaching. Here there are 4 amine ligands, as they're called. These are 4 cyanoligands, cyanide ion. So this coordination number of 4. This has 5, 6, and so on. So the coordination number is the number of attachments. Now, something to be very careful here is that, again, there are going to be some ligands that can attach in more than one place. So one ligand will contribute to multiple coordination numbers. So that's going to be something to watch out for, and I'll talk about that as we move forward. In terms of the geometry of these complexes, so for all the transition metal complexes that have only 2 ligands, those are going to be linear in shape. For those that have 4 ligands, or a coordination number of 4 to be more specific, these could have two possible shapes, either tetrahedral or square planar. And I do have to give you some type of hints about what it will be. Your book has a very small, like 1-sentence blurb about one way in which you could predict whether a compound or a coordination compound is tetrahedral or square planar. However, it's not foolproof, okay? But there are ways that I can let you know which one it is, and I'll be talking about those as we move forward. Finally, if the coordination number is 6, the shape will be octahedral for the coordination compound. So now let's talk about ligands. Again, we can have monodentate ligands, so ligands that have only a single donor atom. And so for monodentate ligands, basically if one of those attaches, it contributes 1 to the coordination number. However, polydentate ligands are those ligands that have multiple donor atoms, and so those ligands can attach in more than one place. And so each place that the ligand attaches is considered a coordination number of 1. So if you have a bidentate ligands, here's some sub-terminology. Bidentate means attaching in 2 places. So these would contribute, it's 2 coordination numbers for this one because it attaches in 2 spots. Now let me give you some pictures to show you what that means. So here we have a variety of monodentate ligands, and the ligand, the atom that is indicated in color here is the donor atom. So they each have 1 donor atom, except for thiocyanate actually. Thiocyanate, even though it's a monodentate ligand, it can attach either at the nitrogen or the sulfur. Now let me explain to you why they're called donor atoms. It's because if you have a transition metal ion and a bond is made here, it is a bond, is made from 2 electrons, right? Well, in a coordinate covalent bond like these, what is happening is that both of the electrons required for the bond are being given by 1 atom. So this bond is made from these 2 electrons here. So we call the ligand that the atom in the ligand that attaches, we call it the donor atom because it donates both electrons to make the bond. And that's referred to as a coordinate covalent bond. And that's why these are called coordination compounds, due to the fact that they're made from coordinate covalent bonds. And so these molecules, you'll notice all the ligand donor atoms have a lone pair on them, at least one, because they need to have those 2 electrons to donate to make the bond. Now, for these are bidentate ligands here, and you see 3 of them. There are others. These are 3 right here. Ethylene diamine, which is often abbreviated EN, glycinate, which is actually a amino acid, and oxalate ion here. So each of these have multiple donor ligand atoms, and they are separated in such a way that they could both attach to the central metal ion. And so keep in mind that these contribute to the coordination number twice, because each one of them will bond with both of its donor atoms here. And there's one very, very useful hexadentate ligand, which is called ethylene diamine tetraacetate, known as EDTA. Super important in all kinds of chemistry. In biomedical applications, it's often used to stabilize, in vaccines, for example. They all have EDTA. They stabilize preservative atoms in there, in the vaccine. They're also useful for environmental applications when you're trying to test for transition metal atoms in like the soil or whatever. You'll combine it with EDTA, which will trap those metal ions, and then you use that fact that they're trapped in this way to help you with your quantitative analysis of these ions. So EDTA is a super important hexadentate ligand. Remember, this is going to contribute 6 coordination numbers. So if one EDTA is attached, what that means is that immediately this compound has a coordination number of 6. Each of these will contribute 2 coordination numbers because each one will attach in 2 places. There will be 2 donor atoms. Now, this ethylene diamine, EN, and EDTA are what are referred to as chelating agents because they attach in multiple places. And the word chelating, it relates to the Latin word crab, which means, and it's like the claw of a crab. So as I mentioned, that for the EDTA, for example, this can basically attach in 6 different places. 2 of these are nitrogens right here, these blue atoms, and 4 of them are oxygens. And they attach in an octahedral fashion and completely surround the central metal ion, which is cobalt here, like a claw. And again, this is useful for isolating those atoms for further analysis later on, or for other reasons, chemical reasons, as I mentioned, in the use of vaccines and so forth. In terms of ethylene diamine, each one attaches in 2 places. So we have one of them here attaching with its 2 nitrogen ions. Then this EDTA here is wrapped around here, attached with these 2 nitrogen ions, and this one here. both of these have coordination number 6 because there are 3 EDTAs. Each is attaching in 2 places. So that is 3 EDTAs, each attached twice, so coordination number 6. And you can tell it's octahedral, the way the nitrogen atoms are arranged around the central cobalt. Here, 1 EDTA attaches in 6 places in this octahedral way around the center atom. So again, coordination number of 6 for just 1 EDTA. Coordination chemistry is actually also happens in your own biology. It's extremely important to many biological processes, including the attachment of oxygen as a ligand to an iron atom on your blood cells. So each of your red blood cells contains 4 of these molecules called heme, which have an iron atom that has 5 nitrogen atoms attached, 4 from this central disk here, and 1 from this right here, and these are all attached to a large protein. And then there's 1 open spot in the octahedron, and that's where the oxygen attaches. And then that oxygen is carried around your bloodstream before it is later released. And so then this is the molecule heme here. And so the result is that basically you can see that transition metal chemistry is super important in biology. It's also important in the electron transport chain, which involves iron and copper ions. So yeah, biology uses this transition metal chemistry all the time. That's why we need some iron in our diet, a little bit of copper. These things are important in small amounts to the functioning of our bodies. So just like for other ionic compounds, we had to name them. We also have to name these coordination compounds, which in many ways they're going to be named like ionic compounds. The big difference is that for these ions that are coordination compounds, they're called complex ions, and they're going to have a little bit more complex name. But otherwise, the naming is going to be the same as other ionic compounds, or salts as they're also called. Just like any other ionic compound or salt, you name the cation first, then you name the anion. Cation means positive ion, right? Anion means negative ion. And so you're going to name the positive ion, then you're going to name the negative ion. The only big difference is that sometimes the positive ion or the negative ion or both are going to have very fancy complex names because they're going to be complex coordination complexes or coordination compounds, as they're also called. So in naming a complex ion, that's a coordination compound, there's going to be various ligands attached to the central transition metal. So for the ligand, they're going to have different names. If it's a ligand that is an anion, that's itself a negative ion, such as bromide ion, carbonate ion, chloride ion, all of these are all negative ions. Their ligand name is going to be like the anion name, but it's going to end with O. So instead of bromide, you say bromo. Instead of carbonate, you say carbonato. Okay, so not carbono, which might be surprising. Instead of chloride, you say chloro. Instead of cyanide, you say cyano. Instead of glycinate, you say glycinito. Instead of oxalate, you say oxalato. So notice that if they end with ate, you just replace the E with an O. But if they end with ide, you replace the whole ide with an O. Thiocyanate, as you might have noticed, if we go back to thiocyanate, it has 2 possible ligand donor atoms. And so generally we name these a different name if they are attaching at a different ligand donor atom. So if the thiocyanate is attaching where the sulfur is, we call it thiocyanato. If it's attaching where the N is, we call it isothiocyanato. Okay, that's also true. Nitrite has that. Nitrite. So nitrite has the same issue. We're going to see it a little bit later, but it's like nitrite is like this. And so for the nitrite, you can have the nitrogen as the ligand donor atom here, or you can have this oxygen here as the ligand donor atom. Either one of those. And so it's going to be the same with nitrite. You have nitro and nitrito. Now, unless you're told which ligand donor atom is attaching, you can use either one. Okay, like nitro or nitrito, or thiocyanato or isothiocyanato. If you're not told which one is attaching, use either one. Finally, if you have a neutral ligand, like ammonia, water, carbon monoxide, or ethylene diamine, they have their own special names, which you have to memorize, unfortunately, sorry. So memorize these. So for ammonia, it's amine. Notice it has two M's, okay, like ammonia does. For water, it's aqua, not too hard to memorize. For carbon monoxide, it's carbonyl. And for ethylene diamine, its shorthand is EN. It's just said ethylene diamine. Now that we know how to name the ligands, if the complex ion has one ligand, you just say the name of the ligand, okay? But if it has more than one ligand, if it's more than one ligand of the same type, we're going to use a Greek prefix like di, tri, tetra, so forth, in order to say how many of those there are, okay? The ligands are going to be listed in alphabetical order where you're not counting the prefixes. So you don't pay attention to di, tri there. You list them in alphabetical order. Now, when you're writing the formula, you can all really write them in any order, but generally you'll see in your book, they write the ligand that there's more than one of, especially if they're polyatomic, they tend to write those first because it looks a little cleaner. But there's not a rule about that, you'll notice here. If the name of the ligand itself has a Greek prefix, like ethylene diamine has di in it, then you don't say diethylene diamine. Instead, you would say bis-ethylene diamine, which indicates two ethylene diamines, or tris. Now, this is an exact copy of the rules given from your book, but something your book fails to mention, which I think is a huge failure in the text, is that bis and tris are also used for any polydentate ligands, not just ethylene diamine. You'll see it in the examples in your book. Like oxalato does not have a di or a tri in it, but still, your book will say bis oxalato or tris oxalato instead of di or tri, and this applies to any polydentate ligands that you might have, including glycinate, thiocyanate, and so forth. Ethylene diamine as well, or EDTA as well. Finally, for your transition metal, you'll use a Roman numeral because they're generally variable charge, right? So you use a Roman numeral to indicate the charge. Finally, if your complex ion is a negative ion, then you're going to replace the name of the metal with the name but with an 8 at the end. And what's particularly tricky here is if you have a name with a Latin root, you use the Latin root. So for those without a Latin root, it's pretty easy. Well, chromium does have a Latin root, but you say aluminate, chromate, cobaltate. But for copper, now you guys know the symbol for copper is Cu, which stands for cuprum. So instead of saying copperate, you say cuprate. Or for gold, the symbol is Au, which comes from the Latin aurum. So instead of saying goldate, you say aurate. And then iron has the symbol Fe, because it comes from the Latin root ferrum. So its anion name is ferrate. Then the rest are pretty obvious here. Manganate for manganese, nickelate, so forth. So let's practice with this now. So let me show you a few examples. So here we have a compound with a complex ion here. So the front is the complex ion. So you can see in the formula for the complex ion, we put brackets around it. And that's very common. So we put brackets around the formula for the complex ion. And so when we write the name here, we're going to write the names of the ligands first, and then the name of the metal. The thing is, we've got to know the charge of the metal So we've got to do a little bit of work here. We got to break this down. So the positive ion is here in the brackets. The negative ion is this one. So you already know the charge of the negative ion. So we got 3 of these. Cl, it's -1. It's chloride. It's a -1 charge. And we've got 3 of them. Okay. And then I've got this whole giant positive ion here. And because I know that this is 3 negative here, I know my positive ion, just like if we were doing nomenclature for ionic compounds, my positive ion here has to have a charge of +3 altogether. Okay? It has to. So because this is 3 negative, I know this must be 3 positive. And there's only one of these here. So the charge on this must be +3. Now, given all of these, so all these charges here have to add up to the total charge. So whatever the charge is for chromium, plus 3 times the charge of ammonia. Now ammonia is a neutral molecule, 0 charge, plus 3 times the charge of water, which is also 0. Those have to add up to +3. So we can finally conclude that the chromium is +3. And so we figured out that the charge of the chromium in this compound is +3. So now we can finally write the name. This one's called amine, and this one's called aqua. So since Am comes before Aq, we're going to write the amine first. So we're going to say triamine. Triamine. So that's a 3 amine, and remember to use 2 M's here. Then we're going to say triaqua, and this is no spaces. Triamine, triaqua. Okay, and then we're going to say, since this is a positive ion, see it's a positive ion, we don't say the chromate, we say just chromium 3. Just like if we were, naming the positive ion chromium 3 without the ligands, we would just say chromium 3. And then finally we write the name of this ion. Since it's a monatomic negative ion, its name ends with "ide", so this ion here, this is called chloride ion, right? So this was the name of the positive ion, this whole big old thing. So you write the name of the positive ion, then you write the name of the negative ion, which is chloride. And that's it. Triamine, triaqua, chromium 3 chloride. Okay, good to go. Let's look at another one. Okay, so often this is written as En, but here it's not, because I wanted you to notice it here. By the way, groups with nitrogen and hydrogen like this are called amine groups. And then this middle part, 2 carbons, is called ethene. So that's why it's called ethylene diamine. This whole thing is ethylene diamine. So we could have just written this as En. But I wanted to point, and usually it is, but I wanted to point out to you that it could be written out completely as well. Okay, so again, we've got a similar job here. We've got to figure out the charge on the platinum. This time it's a little bit more difficult because not all of our ligands are neutral. This chloroligand is actually negative in charge. So let's figure out what the charge is. I'm going to do it all the way over here this time so I don't accidentally write over my other stuff. So I've got 2 chlorides, Cl minus, Cl minus. Okay, and then I've got this whole thing which I'm going to write in the shorthand, PtEn2 Cl2, and we don't know the charge of this right now, but we can figure it out. It's 2 negatives here, so we must have 2 positives, which means that this whole thing here must be +2. Now what we've got to do is figure out what is the oxidation state for the metal ion. And so let's do the math here. We're going to have the platinum here. plus 2 times the charge for the ethylene diamine, which is 0, plus 2 times the charge for the chloro, which is -1 as a ligand. So it's a chloride ion. And that all adds up to +2. And so I'm going to have the platinum charge -2 equals +2. And now if I add 2 to both sides, I get the platinum charge is +4. Okay, so now I can write this. Now, in terms of which ligand I'm going to write first, chloro comes first in the alphabet before ethylene diamine. C comes before E. So I'm going to write the dichloro first. So I write dichloro. And then I'm going to write not diethylene diamine, but bis, because it is a polydentate ligand. Bis-ethylene diamine. And this one only has one M, by the way. Dichloro bis-ethylene diamine. Okay, and this is often indicated in parentheses too as well after the bis. Dichloro bis-ethylene diamine. And then we're going to say not platinate, but platinum, because our ion here is positive in charge. So we say platinum, and then we write its charge, which we determine to be 4 in Roman numerals, IV. Then we write the name of the negative ion, which is just the name of this. That's chloride. So space chloride. So you can see that it follows the same pattern as any other ionic compound, right? Like, write the name of the positive ion, use Roman numeral if it's a variable charge metal, but you have the ligands added at the front. Then you write the name of the negative ion. Okay, name of the positive ion, the name of the negative ion. But the problem is writing the name of the complex ion, which involves writing the names of the ligands before you write the name of the metal. Now you'll also be expected to, if given the name, go to the formula, okay? And look at this one. So this one, notice the positive ion is written first. This is the positive ion, all of this right here. Then there's a space, and then the name of the negative ion is written. So here we have a complex ionic compound that has complex ions as the positive ion and as the negative ion. Okay, so what we have to do is we've got to figure out the charge of each of these ions and then form an ionic compound from each one. So here the first one, which is the positive ion, is going to be it's going to be cobalt with a +3 charge, CO, and then we've got tris ethylene diamine. So we've got ethylene diamine and we've got 3 of them. Now in terms of the charge is going to be the charge of the cobalt, which is +3. So we'll say +3 plus 3 times the charge of ethylene diamine, which is a neutral molecule, 0 charge. So the charge is going to be +3 here. So the charge on this entire ion is 3+, this complex ion. Now, the next we're going to have a complex ion that is negative. You can tell it's negative because it has 8 at the end of the name there. And the transition metal in that complex ion is going to be manganese, Mn, and it says pentacyano, so 5 cyanides, Cn, 5 of them, iodo, 1 iodo ligand. And we don't know the charge, but we can figure it out. The manganate, it says manganate 2, which means the manganese has charge +2. And then we got 5 cyanide ions. Cyanide have charge of -1. And we have 1 iodo ion that has a charge of -1 as well. And so those charges all together are 2 minus 5. So that's -3 minus 1 more, -4. So the charge on this negative ion is 4 minus. And so if we are going to make a compound from these, we have to make it neutral, which means we'll need 4 of these positive ions to make 12 positive charges. And we'll need 3 of these negative ions to make 12 negative charges. So our compound altogether is COEN3, 4 of them, and then the MnCnI, 3 of them. That makes the neutral ionic compound. So there's an example of one with a complex ion for both the positive and the negative ion. And note, when we have the name for the negative ion, when it's a negative complex ion, the name of the metal gets an 8 at the end of it. Oh, whoops, and behind my head there. +2, +5, -1. I cover it up in my head a little bit. And then finally, pentaamine chloroplatinum 4 bromide. Okay, so for this one, again, so notice what we did here to write the formula. We write out the ions just like if we were doing nomenclature of ionic compounds and writing the formulas. Then we make sure that we have enough of each so that the charges cancel, just like we were doing any other ionic compound. The big difference is that these ions are more complex. So finally, we have pentaamine chloroplatinum 4. Okay, so this is going to be have PT, and it's going to have pentaamine, so 5 amines, and then it's going to have 1 chloro. And we don't know the charge, but we can figure it out. The other ion is bromide. So bromide ion, the ide tells you it's monatomic, and monatomic bromide ions have a -1 charge. Now to get the charge here, we have that the platinum is told to us to be +4, so this is +4, and that's going to be +5 times ammonia molecules are neutral with 0 charge, +1 times a -1 charge for the chloro ligand, and so it's going to be +4 -1, so that's altogether +3. So we can write the charge now up here. It is 3 plus. And so to have a neutral compound, we're going to need 3 bromides so that we have 3 negative charges. So we write this as this whole one and then 3 of the bromides. So right here, this whole ion, the positive ion, which is +3, and then we need 3 bromides, Br minus, Br minus, Br minus. That gives us 3 negative charges altogether. So that's why we have 3 bromides here as the negative ions, and that gives us the neutral ionic compound. And so that's how you handle the nomenclature of these complex ions. So on the big picture, remember that it's just like any other ionic compound. You're going to have, if you have a neutral ionic compound, you've got to have enough of the positive and negative ions to cancel the charges. The only difference is that for the complex ions, we have to write the name of the ligands with prefixes to tell how many before we write the name of the transition metal and also indicate its charge, which you can have to figure out based on the total charge of the ion. And then finally, if you have a complex negative ion, it's the name for the metal is going to end with 8. So notice that's never true for the positive ions, right? Platinum when it's a positive ion, chromium when it's a positive ion, cobalt when the complex ion is positive. But when the complex ion is negative, like this one here, we say manganate at the end because this complex ion is negative. So that's how you name these these coordination complexes. So what are they going to look like? So this is where we're going to talk a little bit about the shapes of them and the ways in which the ligands can attach to one another. The result of these shapes is that there are a number of possible isomers for many of these coordination compounds. So just recall what isomers means. They're compounds, they have the same formula, same atoms in them, but those atoms are arranged in a different way. Now, out of the large group of, the large terminology here of isomers, there's 2 subgroups of isomers. They can be constitutional isomers, which means that, again, the atoms are the same, but the way in which they're connected together is different. So this may be with the ligands themselves. They might be bonding at a different atom. So as you saw, some ligands have multiple possible ligand donor atoms. And so if they're attached at a different ligand donor atom, those would be linkage isomers. There can also be ionization isomers, which means that in the different isomers, the different ions are ligands versus being negative ions, for example. I'll show you some examples of that. And then on the other side, there's stereoisomers. So here, all the connections are the same. So the atoms are connected with the same other atoms, but the way that they're arranged in three-dimensional space is different. And this comes in two subgroups. The first being enantiomers, which are mirror images of one another and have different 3D arrangements, and diastereomers, which have different 3D arrangements but are not mirror images of one another. So let's talk about the different situations in which you might have these types of isomers. The first example is linkage isomer, and so we can see here with this cobalt compound, it has a nitro ligand, nitro and nitrito ligands, and it's the difference here is where they're attached. Here the nitrogen is bonded to the carbon, but here the oxygen is bonded to the carbon. So it has all the same atoms, all the same ligands. It's just for one of these ligands here, the ligand donor atom is different. So that's an example of a linkage isomer. And the result is that the compounds will have different properties. You can see here these have a different color to them. And that's the result of being linkage isomers. The other is ionization isomers. So in ionization isomers, the status of an ion, and usually a negative ion, as either being a ligand or the negative counter ion is different. So here we say that this has a free sulfate ion, because if you dissolve this ionic compound in water, what you're going to get is you're going to get this ion, this complex ion, CONH3 Br, and this is going to be +2, and you'll have a sulfate ion, which is -2, okay? And the sulfate ion will be free. Is it aqueous, right? So this is a free sulfate ion. It's not one of the ligands in the complex ion. Here we have the opposite case. The bromide ion is free. So here this would be CONH3SO4, and this is +1, and the bromide is -1. Now the bromide ion is free. It's no longer a ligand. So here the sulfate ion is the ligand, and the bromide ion is the negative counter ion in the ionic compound. And so these are ionization isomers in which the ligand and the negative ion in the compound are in different spots. Next are various types of stereoisomers. So what is possible for stereoisomers depends on the geometry of the compound. So if we have a square planar compound, it is possible for it to have stereoisomers. This is only, so you can see the examples of square planar compounds, because it's not possible for tetrahedral compounds to have this kind of isomer. So these are a special kind of diastereomer called cis-trans isomers. And the difference here is that since this isn't a square arrangement, you can either have a particular ligands across ways from each other or at 90-degree angles. So here the chloroligands are next to each other at 90-degree angles, and so are the amine ligands. So these are called the cis isomers because the same ligands are on the same side. Whereas the trans isomer here, they're opposite one another. So these are 180 degrees from each other, these chloroligands, and these amine ligands are 180 degrees from one another. So that's a kind of diastereomer called a cis-trans isomer. So notice these are different from constitutional isomers because in both of these isomers, 2 amines are attached and 2 chloros are attached to the platinum. So all the attachments are the same. The difference is their arrangement in 3-dimensional space. Here, these are arranged opposite one another. Here, they're arranged next to one another. This does not happen with tetrahedral arrangements because there's no opposite every space is equivalent to every other space. And so this kind of isomerism only happens in square planar compounds. Or it can happen in octahedral. So I'll say this doesn't happen for tetrahedral. Now here's an example of diastereomers for an octahedral complex. So again, in the octahedral complex, there are 6 possible arrangements, and we have the same situation where we can have 2 of the same ligand, like the chloro one here, 90 degrees from each other, next to each other, and that would be this position or this. There's 3 possible positions that are 90 degrees away from this one right here. So for example, if we rotate this, we rotate it so the chloro is up here, it's still the same isomer. It was just rotated around. So these are not isomers of one another. These are the same molecules. But this is a different isomer here, because here the chloro is 180 degrees from the other chloro. They're on opposite sides of each other. So these are the cis isomer here, where the chloros are next to each other. These are the trans isomers, where the chloros are opposite one another. And so again, you can have these situations with square planar compounds or octahedral compounds. You can't have them with tetrahedral compounds because you don't have different spots like this. All the spots are the same in the tetrahedral compound. Finally, we'll talk about enantiomers. So molecules that can have enantiomers are also referred to as chirals. Chiral is referring to the Latin word for handedness, hands. And so these are mirror images of one another, like your hands are. Your hands are mirror images of one another, but they're not the same because the thumbs are on different sides. These are non-superimposable mirror images that are non-superimposable because they're the same if by mirror, but they're not the same if you try to stack them. That is a chiral object. So not all objects are chiral. Hands are chiral, but a lot of others aren't. Objects that are not chiral because they have a plane of symmetry through them that can divide them into 2 pieces that are exactly the same. A chiral object like your hand, you cannot split it in half in any way that it would be the same both halves, because there's a front and a back and a side and a side. So no way you cut it will the 2 sides that you cut be the same. And so objects that do not have a plane of symmetry are chiral, like your hands. So there's a couple ways in which you can get a molecule that has chirality. One of them is if you have 3 bidentate ligands in this fashion, and this one is very difficult to see. However, if you were to take this and to rotate this, it would not be the same. And this is because of the way that these ligands are attached to one another. So if you have the mirror image here, and if you try to rotate this, so you can see on this one, we're going straight to from the bottom out. This represents coming out of the page towards us. However, if we were to take the mirror image and rotate it and flip it, what you would find is that this would actually be coming from the back of the page. So if we rotated this all the way around, this nitrogen would be on the back of the page instead of being on the front. And so we would have a mirror image here that is not superimposable. So one way to have an enantiomer is to have a molecule with a coordination number of 6 like this with 3 bidentate ligands. Notice that if you have 6 monodentate ligands, like the amine ligands here, there's a plane of symmetry. You're not going to have an enantiomer. So that's the first situation. If you have a octahedral complex like this with 3 bidentate ligands, you'll have an enantiomer. The other situation that's very common is if you have a tetrahedral molecule with 4 different ligands. And I'm going to build that one for you in mole view. So let me show you mole view. Here, mole view. So MolView is a really nice tool that you can use to build things. It's not going to work for you all the time, but it's pretty handy for building things so you can see the shape. If you want to build something tetrahedral, you can just use carbon. And if you click on the carbon, it will make it will make more bonds, or it should. Just click on the bond here, and it'll make bonds like this. And then you can put different atoms attached to it, like hydrogen. I like to put halogens since they only want to bond once. Okay, like that. And then if you click 2D to 3D, it will make a shape. So here's your tetrahedral shape. Now, if I make the mirror image of this, so let's say I have the mirror image right here. If I rotate this to stack on the mirror image, the difference here is that these two atoms would be switched. Okay, and so if you have a tetrahedral complex with 4 different things attached, 4 different ligands, you will have an enantiomer. Or if you have like this, a octahedral complex with 3 bidentate ligands attached. Those are the 2 situations in which you can expect enantiomers. So what is the big deal with enantiomers? Well, it's really important in medical chemistry because often one enantiomer of a compound is biologically effective and one is not. And enantiomer compounds are very difficult to separate from one another because they tend to have all the same physical and chemical properties, except for in 2 situations. Number 1, they react biologically in a different way because the proteins that do the biology are also have enantiomers and can only react with one. The other thing is that if you put them in a tube and pass polarized light through them, you guys have probably heard of polarized glasses. What it does is it selects light that's only traveling up and down, let's say here like this. It selects the up and down light. You pass this through, it will rotate the plane of the polarized light. So you can have another polarized glasses here and you rotate that with a measuring instrument to find out how until you see the light coming through. And that can tell you how much the rotation of the plane polarized light would be. But otherwise, there's no other properties that can help you to tell the difference between 2 enantiomers of one another. So they can be very difficult to separate, and that's one of the big challenges of pharmaceutical chemistry, is separating enantiomers from one another. But let's do a little bit of a practice here. So which one of the following complexes can exhibit geometrical isomerism, or constitutional isomerism, as it's also called? So so what I mean, sorry, geometric constitutional isomerism. Why is it doing this? The geometrical isomer, or diastereomers, cis-trans isomers. Cis-trans isomers. Okay. So for one thing, if we have S, I'm going to do B first. So here we have tetrahedral. All of these are the same, so I'll build it in MolView to take a look. This is probably the hardest part. If you guys want to go out and buy, models to do this, you'll need them in organic chemistry, or they're useful in organic chemistry. You could do that, but you don't have to. You can use MolView here. I'm going to show you an example where we have a tetrahedral complex with 2 of one ligand and 2 of another. And so you'll see here that if I were to move these, so let's say I move these 2, I'm going to move on my Lewis structure here. I'm going to move the chlorine to be where the bromine is. Because this is tetrahedral, it doesn't make any difference, okay? All these spots are the same, so I can rotate this to be just like it was if I move these around. These are not diastereomers of one another. These are not geometrical isomers, okay? And so this one does not have geometrical isomers, the tetrahedral one. This one, it's square planar, but all of the ligands are the same. So if you switch them, you're not going to have cis-trans isomers. They're all the same. This one's octahedral. It has 5 of one ligand and 1 of another. If you switch places, it's not going to make any difference here. The one that will make a difference is the one that's square planar. This one's linear, so again, you've got something in the middle connected to 2 things on the side. Well, they're the same thing anyway, so if you switch their places, you've got the same thing. But this one's square planar, so you've got the transition metal ion in the middle, and then you've got 2 different ligands. So with this ligand, there could be, let's say, the blue ones here and here, and the black ones here and here. And this would be a trans isomer because it's flat, it's square planar. Right? Or you could have black ones next to each other. These are all 90-degree angles. And the blue ones next to each other like this. This would be the cis isomer. So this is the one that can have the geometrical diastereomers or cis-trans isomers. The square planar. So when you're doing these, I encourage you to, go on MolView, try making some complexes, especially the tetrahedral ones are the really hard ones to see. So really, the tetrahedral, the only time you're going to have isomers is if you have enantiomers, and that will happen when you have 4 different ligands attached. So that's the only time you have to worry about that. The cis-trans isomers can happen for square planar complexes or octahedral complexes. Here, if you have 2 and 2, it won't happen if you have 1. Imagine one of these was blue now. Well, now it doesn't matter where you put the black one, because if I put the black one over here, I can just rotate this and I'll get the exact same thing again. So those wouldn't be isomers, they would be the same molecule. But if you got 2 and 2, like we did before, then, like making this black again, well, now we can have cis-trans isomers. And when it comes to octahedral, again, if you have just 1, you can just switch that someplace else, but if you rotate the molecule, you're going to have the same thing. So you need to have at least 2 of a different isomer. 3 and 3 can also produce cis-trans isomers. And that's isomers. And so now we've talked about how to name transition metal complexes and the way in which they're shaped. Our last topic for this chapter is going to be about the theory behind why they are colorful. And so we're going to talk about the color of transition metal complexes and the various theories we can use to describe their chemical behavior. And so that's it for this lecture, and I'll see you in the next one. All right. Bye. I have to fix my cable here because the kitty's messed it up, so I can stop recording. I'll see you guys next time.